Okay, first just an announcement about the calculus specific part of the final exam. The calculus specific part will have one question from today's lecture and then one question from the material that was covered on, from chapters 1 through 15, the material that we covered for the last exam period. So there'll be two calculus-based questions on this rather than one. I have the non-calculus-based test already written. As I was telling Caitlin, it took me 15 minutes to solve it. I know it's going to take you a lot longer than that, right? Because you're not the teacher. But hopefully students don't feel time pressure because there's only 2 hours for the final test period, whereas we've been using 3 for the other test periods. But I do think this one will take people less time. Question?
How many total questions are there on the
It's 10 again.
Okay. I was looking back and there was like one where you did 7 or something.
No.
Maybe there's something wrong.
Yeah, it may have been missing a page or something.
Okay.
I've done 11 or 12, but I've not done 7.
Okay.
Okay. Any other questions about that very brief description?
Will be graded by Thursday, so we know.
Oh, yeah. My initial plan was to try to have them graded by Thursday. But at this point, I would be willing to bet my house that won't happen. And, of course, I'm not working to make that happen, not working to win that bet. But, it takes too long to grade.
But how do we
Know if you need to take the final exam or not. I know because that hurts me more than it hurts you. Because it doesn't hurt you to take final exam. It hurts me to have to grade. I don't have any answer on that. Because, you don't want to, I was, if I got 57% on this exam, I would have raised my grade. You don't want to be in that situation if I chose not to and didn't know. So I understand the complexity of that situation. Not in my defense, but just to give you another viewpoint, there are some teachers who don't like students to be able to calculate what their final grade would be for different scores on the test because they want them to come in and do their best every time. So if I was of that, I do want you to do your best, but I also think that it's fair for people to know, but I don't think I'll be able to. I'm sorry.
So when are you guessing that?
Maybe Monday morning after, grading on all day Sunday and Thursday.
This final's Tuesday.
Yeah. I sure hope. I do my best. Like a sumo wrestler. What are you going to do? I will do my best. I see you won. What did you do differently? I did my best. Okay, so let's talk about damped harmonic oscillators. But before we talk about the damped harmonic oscillators, we have to talk about the undamped. Now, today's lecture has a lot of differential equations in it. Now, you guys aren't supposed to know differential equations, right? It's not something you're responsible for. So I'm not going through and saying, and this is how you solve the differential equation. But we'll be going through and looking at the solution. Notice I changed that from a C to a B because I like to use B for the damping constant, and that picture used a C. So we start by having a spring that's holding a bob. And notice the direction down is considered positive in this picture, and I'm going to be consistent with that. And the first thing we're going to do is apply Newton's second law to this bob. So if I'm going to apply Newton's second law to this bob, what do I need to do first? What should I do before applying Newton's second law? Free body diagram. Now this picture shows 2 forces out of the 3, but we're doing it initially saying, what if there's no damping force? So one of those forces we won't have. So I'm just going to draw my bob, which is just the ball. And the forces acting on that ball are, and name them for me. Gravity, which points? Down. So I have a downward force, force of gravity equals mg. And if that spring is pulled down below equilibrium, what other force is it going to have on it? Force of the spring, which will be pointing up. Force of spring has a magnitude of kx. Notice I said it has a magnitude. I showed my vector giving the direction. And that x is going to be how much it is stretched down as illustrated in this picture from the equilibrium position. So now, Newton's second law. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. So looking at my picture, that's mg minus kx. There's the sum of my forces. I use down as positive, so that's why mg is positive. Up is negative, so my force of the spring was negative. Now I'm going to solve this for the acceleration. Actually, I'm going to solve it for equals everything with x is on one side and everything without x is on the other. But I also want the acceleration to not have a coefficient, or to have a coefficient of 1 if you prefer. That's what I was meaning when I said I'm going to solve for acceleration, but not exactly. So I'm going to move this across. So I'm going to add kx to both sides. And then I'm going to divide everything by m. So I have ax plus k over mx equals g. And now the last step is simply understanding, yes, this is a calculus-based class. AX means something specific to us since we know calculus. What does AX mean to us since we know calculus?
Your second derivative position.
So we have d second x dt squared plus k over mx is equal to g. So this is a second order linear differential equation. Why is it second order? Because the highest derivative is the second derivative. Why is it linear? Because I don't have x squared or the derivative squared or anything like that. It's all just linear terms. So how do we solve this? You've not taken differential equations. I don't expect you to know the answer to that question. Instead, we look at, hey, look, there's the same work I just did. And we say, well, there's going to be two solutions. Why two solutions? When I was in differential equations, I was a little confused about this. Why do I have to solve it twice? Well, you have, if I had that equation, the left side equals 0, I can get a solution for that. And we call that the homogeneous solution. If I have the left side equals g, I will get a different solution, and we call that the particular solution, because it's particular to whatever I had on the right side. But if I have the homogeneous equation, the one that's equal to 0, since the left side's equal to 0, it wouldn't change the right side. And so my solution is actually the sum of the linear combination of the solution for the homogeneous equation plus the solution for the particular equation. So we have to actually find two solutions and just put them together. So let's look at the two solutions. First, the particular solution. Because we have this differential equation, we have some function, its second derivative, plus the original function times a constant is equal to a constant. Well, that's actually a really easy solution. You're going to have something that is linear, or excuse me, not linear, but that doesn't have time in it, or else you would have something with time on the left side equal something without time on the right side. So your function has to be without time. It has to be a constant. And so if it's a constant, the second derivative is going to have to be 0. Right? Second derivative constant is always 0. And so then I just solve this for x particular, and there's my particular solution. What does that x particular actually represent? That represents the distance the spring is stretched when it's at equilibrium. Right? It's a simple little calculation. So that's my particular solution. And when you take differential equations, you're going to have to find the particular solution. You'll have to find if you take, I should say, not when. You'll have to find the homogeneous. And the homogeneous is the one you spend the time on. The particular can be difficult, can be easy. This was easy. The homogeneous solution. Once you've taken differential equations, you go through and you find that for a second order linear differential equation, your solution has the form of e raised to the ct. It's an exponential solution. And in fact, for any order of linear linear order differential equation, that's the solution. You can have, first order, second order, third order. If it was first order, we actually could have solved it. But so we have this. Now I put down here, we're going to find that there are two solutions, and so our total solution for the homogeneous will be the linear combination of the two solutions. But I need to find what those two solutions are. So I find those two solutions, and it's done on the top of the next page, but I'm going to do it here, by taking this function and plugging it into my equation. Right? Since I know the answer has a certain form, I'm going to take that answer and put it into the equation and see what I get. So I have to have my x, and I have to have its second derivative. Can you find the second derivative of that x? It's what? Well, what do you do when you take the derivative of an exponential? You bring down the derivative of the exponent. So what's the derivative of ct? It's not 0. Derivative of ct is c. And so the first derivative is c e to the ct. Second derivative is going to be c squared e to the ct. So I can do this, x dot is equal to c e to the ct. So x double dot is equal to c squared e to the ct, which is also x squared times x homogeneous, since the e to the ct was my x homogeneous. So now if I put that into my equation, I'm going to have So I have this equation. I actually should have put it like in a different color. My x homogeneous times factored out c squared plus k over m is equal to 0. There are two conditions that would make this true. One of them we call the trivial solution. What would be the trivial solution that would make this true? Yeah. The trivial solution is if xh is equal to 0, then this is always going to be true because I'd have 0 times that parentheses equal to 0. We call it the trivial solution because it's pretty much always true and never useful. Right? So like when you're taking differential equations, especially if your teacher's a stickler, like if I was your teacher, I've had to teach this a few times, it's important that you point out, yes, there is this trivial solution, but it's not useful to me because that would mean it's not oscillating. And I want to find about its equation when it is oscillating. So the other condition is c squared plus k over m equals 0. Well, let's solve that for c. If that's c squared, then what is c going to equal? C is equal to plus or minus the square root of minus k over m. You have to have plus or minus because whenever you take a square root, you have a plus or minus. Square root of a negative value, right? K is a positive. M is a positive. So that's definitely the square root of a negative value. What do you get when you do a square root of a negative value? Imaginary number. Didn't you like it when you were in grade school and it was just, you can't do that? You know, if you get along in life and start taking particle physics, you'll see that we have these calculations that, well, there's no solution if you use real numbers. Oh, and there's no solution if you use imaginary numbers. So let's try a matrix. Oh, well, if we use a 4 by, then we can get a solution. There's really ingenious mathematicians out there. And yeah, I'm not one of them. Not yet. So there's our two solutions, one with a plus sign, one with a minus sign. So here I've written it out. We call the undamped natural frequency omega sub 0, and that's square root k over m. And then we have C plus, the one with the plus sign is the imaginary number I times that undamped natural frequency, and the C with the minus sign has a minus sign. You see how that works, right? And so the linear combination of these two solutions give me x homogeneous is equal to some constant that right now is an unspecified constant times the first solution plus some other constant, right now unspecified, times the second solution. What are the values for A and B? Those are going to be set by your initial conditions. It depends on how much the spring is stretched and how fast it's moving at time equals 0. So we call those the boundary conditions. Your boundary condition of the position at time 0 and the speed at time 0 are what set A and B. So A and B are parameters that will depend on how you start the system. Well, a lot of people aren't super comfortable with an equation that looks like that. But how many people know Euler's equation? How many people know how to spell Euler? One. Or Euler's formula, I should have said. There's how you spell Euler, E-U-L-E-R. And he has this equation that says e to an imaginary number is really just a combination of cosine and sine. So e to the I theta is equal to cosine theta plus I sine theta, which makes physicists ask silly questions on tests like, what is the value of I raised to the I power? I'm pretty sure only physicists ask this question on tests. The way we expect you to solve that is to say, well, I is equal to e to the, if you notice here, if theta is pi over 2, then e to the I pi over 2 is equal to I. And of course, if you increase by 2 pi, you'll get around to it again. And so that is a function that tells you I. It's a multi-valued function. We're going to get more than one answer. Oftentimes, like I've actually seen this question asked on tests and they expect you to use the case where n equals 0. There's also another solution. It's equal to minus e I times that's also correct. So there's a whole lot of solutions. But let's just start with the easy one. Let's just say e to the I pi over 2 is equal to I. So if that's I, then what's I squared equal, or I raised to the I power equal to? And what do you do if you have e raised to some power raised to the I? You multiply the exponents. But of course, e to the I squared pi over 2 is e to the minus pi over 2. And you can put that in your calculator and you can get a number. So when I was in college, a homework problem I had to do was, obviously you remember these because they're so odd. You look in the want ads in the newspaper and somebody is selling his car for I raised to the I power. Yeah, it gives specifications on the car. is this a good price? Should you go buy it? And, if it's e to the minus pi over 2, yeah, that's really cheap. But you could have, n is equal to, if you use the lower one and n's a really big negative, if n's a really big negative number, then it's going to be really expensive because it's multi-valued. Okay, enough of that. That's just math talk. So with Euler's equation, e to the I theta is cosine of theta plus I sine theta. Now, something you should keep in mind is if I'm talking about the position of my simple harmonic oscillator, it doesn't have an imaginary position, does it? It only has a real position. So we have a bit of a restriction, and that is the imaginary part has to be 0 from this. So it's easiest to take that Euler equation and just do the expansion. So if I do the expansion, this is equal to A times cosine of omega naught t plus I sine of omega naught t plus B. I'm going to actually change colors here. So there I've made the direct substitution using Euler's formula in both cases. But if I look at this, I have cosine occurring two places. What's cosine of negative omega naught t? It's exactly the same as cosine of plus omega naught t, right? Because cosine is a symmetric function. Did I say that right? Yes. Okay, so I'm just going to change that to a plus sign because it's no different. What about sine of minus omega naught t? That's negative sine of plus. So I'm going to change this to a plus sign here and change this out here to a minus sign. And now I can combine these to have a plus b cosine of omega naught t plus I times a minus b sine of omega naught t. Now, a and b were just constants that depended on our starting condition. So I can consider a plus b a new constant and a minus b a new constant. Of course, a and b didn't have to be real numbers, did they? No. I never specified that. So I can't say that a minus b means that a plus b is 2ab because the a minus b, well, actually, I can, but we have two new constants that we just call d or c. Let c equal a plus b, and that's a d. Let d equal I times a minus b, and we're good to go. So we just say these are our new constants. We know that d, I'm going to now say d has to be a real value because I've taken the I out of it, and I need to have my actual amplitude is real. And so d is a real number. A and b, since a minus b has to give me a real, well, if you look at these are both reals. So that tells me, I'm not going to go through the math. It's pretty simple. It tells me that the complex part of A and the complex part of B have to be opposite signs, and the real part of A and the real part of B have to be the same thing, but it's not important. We just have these new constants C and D. Or we can go one step further, because C cosine omega naught t plus D sine omega naught t still gives you a sinusoidal function with a different amplitude, F, and a phase angle, phi. And so we can write it many different ways. The way that's most convenient usually is to put it in this form. But, it's up to you which one you choose. What's the important outcome of this? We have a sinusoidal function. That's the important outcome. And that sinusoidal function has a natural frequency of omega naught is square root k over m. So that's the solution for the undamped simple harmonic oscillator. And you see there's a lot of math that goes into it. Some of it complicated, the differential equations. Some of it simple using the Euler's formula and rearranging it. Why did I do that? Well, number one, because you kind of need to know. Number two, because now we're going to come back and we're going to put in the damping force. So I'm going to go back and draw my free body diagram again, but this time I'm going to have everything in it. So here's my object. I'm going to have the same forces I had before. So I had force of gravity equals mg. The force of the spring equals kx. And then I have one more force, and that was shown in my picture as well. Once again, change that from a C to a B. And so that additional force that I did not have before is the force damping is equal to BV. And once again, I've used the direction of my arrow to indicate the direction of the force. When V is a positive downward value, it's going to be an upward force. And so I've drawn my free body diagram. What's the next step? And so looking at my picture now, I'm going to have mg minus bv minus kx equals max. Rearrange, yes, question, Gabriel.
I'm curious what we're summing the forces with respect to x instead of y.
Well, because I defined x as the downward direction.
Oh, I see.
Yeah. Well, I mean, that's a good question, right? Why don't we go ahead and do it in the vertical direction? It seems to be oscillating that way. All right, so I'll rearrange it just like I did last time. So I will have ax plus b over mv plus k over mx equals g. And since this is a calculus class, the first calculus is, and I'm going to write it this way because it's easier, x double dot plus b over m x dot plus k over m x equals g. What does it mean to say x double dot? Second derivative with respect to time. If it was x prime prime, that would have been with respect to position. That's a physics convention, right? In a calculus textbook, they could go, the dot could mean with respect to position, the apostrophe or whatever could mean with respect to time. But in physics, dot means time. So that's x double dot is second derivative position with respect to time. X dot is first derivative position with respect to time. And then we have x. So this is, once again, a second order linear differential equation. And once again, the solution has the form of e to the ct. And once again, I'll have the same homogeneous solution. So pretty much everything we did before applies, except if x homogeneous is equal to e to the ct, then x dot homogeneous is equal to c e to the ct, which is equal to cx homogeneous. X double dot homogeneous is c squared. So if I put those all into my differential equation, I'm going to have x homogeneous times c squared plus x homogeneous times b over mc plus x homogeneous k over m equals 0. Why did I put equals 0?
That's what homogeneous.
Because that's what homogeneous means, yes. So for the homogeneous solution, it's equal to 0. And so I have this equation, which just like before, I can factor out the x homogeneous. And I have this condition. Two solutions. What's the first one? X homogeneous is 0. Okay, that's the trivial one. We just acknowledge it exists and it's not useful to us. And we go on to the other solution. And this actually has two solutions because it's a second-rank polynomial. And so how do we solve this polynomial? Yeah, that's right. So C equals negative parenthesis B over M plus or minus the square root of parenthesis B over M quantity squared minus 4 times 1 times K over M all over 2. Well, we like to bring that 2 into the numerator. And so this is equal to minus B over 2M plus or minus the square root of B over 2M quantity squared. Notice when you bring the 2 into the square root, it has to be squared. And then in the next term, I had minus 4. Well, 4 divided by 2 squared is 1. So that's my solution. Now let's use an abbreviation. Let us just define alpha is B over 2M, which is what we call the neper frequency. All my life, well, ever since I was your age, I've known that that was the neper frequency, but I finally looked up today why it's called the neper frequency. It's called the neper frequency because John Napier, N-A-P-I-E-R, I don't know, if you're French it may be pronounced differently. John Napier is the one who developed logarithms, and that is the exponential decay or attenuation constant, and so it's named after him. So we call this the neper frequency, and of course we already have defined that omega naught was the square root of K over M. That was the natural frequency if it was undamped. And so using those, I could say C is equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. Now that's two solutions. Minus alpha plus the square root thing and minus alpha minus the square root thing. Now let's go to the next page where I've written in, well, actually I've done the work of this page and gotten to this solution. So here's what we just worked out right there. So what do we do with this? This is where the differential equations becomes a little more interesting. Why a little more interesting? Because we have 3 different solutions that come about based on the value of B, based on the value of that damping constant. And so we have to look at each of those conditions separately. Why do we have the different conditions? Let me go back a slide. We have the different conditions because if alpha is greater than omega naught, then we have a real value for that square root. Real root. If alpha is less than omega naught, then we have an imaginary root. And as we saw from the undamped situation, if we have an imaginary root, that means we're going to have sinusoidal oscillations. If we have a real root, we don't. So that's two conditions, and I said there are three solutions. If it's equal, if alpha is equal to omega 0, then there's only one root, right? I just have minus alpha plus or minus 0. And so that's the third solution. And we're not going to go into the theory of why the third solution is as weird as it is. We'll just say it is. Differential equations, you'll learn why. Once again, if you take it. So looking at the three solutions, the first one, the underdamped. The underdamped is for small damping. So if you have small damping, then it will be underdamped, and you have that condition that alpha is a bigger value than omega. Or excuse me, alpha is a smaller value than omega. Wow, I said that wrong. Small b alpha equals b over 2m is less than. So those are the conditions for underdamped. In that case, I define my resonant frequency as the square root of omega naught squared minus alpha squared. Why, you say, why? Well, let's remember, C is minus alpha plus or minus square root of alpha squared minus omega naught squared. If alpha is less than omega naught, then that's going to be a negative value. And so I could rewrite this as minus alpha plus or minus the square root of minus 1 times omega naught squared minus alpha squared, which is equal to minus alpha plus or minus I square root of omega naught squared minus alpha squared. And so this here we define as my new resonant frequency. So notice this is going to have a resonant frequency. The frequency that it oscillates when it's damped is not the same as the frequency it oscillates when it's undamped. It's shifted a little bit because of that damping. Is it shifted to a higher or lower frequency because of the damping? Is omega r bigger or smaller than omega naught? It's got to be smaller because it was omega naught squared minus something. So the new resonant frequency, if you damp it, is actually a little bit lower frequency. Now we have two pieces, and so we have C plus is equal to minus alpha plus I omega resonant, and C minus is equal to minus alpha minus I omega resonant. And so using the Euler formula, I'm going to have x plus is equal to e to the minus alpha e to the plus I omega r is equal to e to the minus alpha times cosine of omega r. Oops, I forgot the t. Okay. Hopefully you can tell what I wrote. And so that's my x plus. What's the difference between my x plus and my x minus? Anyone? Euler? I have that minus sign, the exponent, so that's going to be doing my math in my head. I applied our rules for cosine of minus omega RT is equal to cosine of plus omega RT, and sine of minus omega RT is minus sine of omega RT to get that. So those are my two solutions. I take the linear combination of them, so I multiply the first one by a constant, the second one by a constant, add them together, and that's going to give me this here in the simple form, or this here in the most reduced form. So you have two pieces here. This piece here tells you the amplitude at any time. And the amplitude is decreasing with your neper frequency alpha, the attenuation frequency alpha, if you will. And so you have, in the picture there, it has A instead of F for the constant. But you have the amplitude is the dotted blue lines. And then you have the sinusoid that's oscillating inside of there that has that form. So that's your underdamped solution. See how you get it now. So that's underdamped. Go to overdamped. For overdamped now, we have large damping factor, large B, so alpha equals B over 2m, is greater than omega naught. And then we're going to have the second term in C is real. And so I have just C is equal to minus alpha plus or minus the square root factor, which we just call beta to make life shorter. You know, less work involved writing beta than square root alpha squared minus omega naught squared. And so this here is my solution. So when you plot it out, you have an exponential decay multiplied by an exponential increase plus an exponential decay. Well, when you put those together, pretty much the B even minus beta t is usually going to be meaningless unless A is much smaller than B. But you have a kind of stretched logarithmic decay, and it takes a very long time for it to reach zero because it's overdamped. What happens is you just have a lot of resistance to motion, so from its maximum displacement, it just very slowly comes back toward equilibrium. And then the third solution, the tricky one. I know, you might have said, what? Those weren't tricky? Well, the third solution, when you have alpha equals omega naught, then we had C is equal to minus alpha plus or minus the square root of alpha squared minus omega naught squared is just equal to minus alpha. We only have one root. And at that point, you're really tempted to say, well, that should be easy then because I just have one term, not two terms I have to add together. And this is where I said I would leave it to a differential equations class to show you why. But in such a case, it turns out that your solution is a polynomial of the rank of the degeneracy. Degeneracy is how many times you have the same solution multiplied by the solution. And so this here has a degeneracy of 2, or, well, actually I should have said rank minus 1, because it had degeneracy of 2. There are 2 degenerate C values. And so you have a polynomial that goes first, time raised to the 0 power, and then time raised to the first. So going up to the degeneracy minus 1. And so my solution is there's the polynomial part, and here's the exponential decay part. And it turns out this critical damping is the quickest one to reach 0 and stay at 0. Underdamping gets to 0 fastest, but oscillates around 0. Critical damping gets to 0 and stays at 0 the fastest. Overdamp takes a long time to get to 0. So those are our 3 different types of solutions. Now, what might you have that deals with this for the test? I am not going to ask you to solve any differential equations, right? That's outside the scope of this class. But what I can do is ask you to take this differential equation and knowing the solution is of the form e to the ct, find the solution if it's underdamped, or find the solution if it's overdamped. What do you have to do in those situations? There is calculus involved.
Guess and check.
Guess and check is almost right. You have to take the first and second derivatives and plug them into the equation and check. So it's not guess, it's take the first and second derivatives, but it's still and check. So that's the kind of problem I could give you with this, something that has you take the general solution and see what the specific values are going to be for, alpha, omega, etc. Something I won't have you do, just because it takes more time to explain than we have in our 5 remaining minutes, is I could say if x at time equals 0 is equal to 5 and v at time equals 0 is equal to -3, got to have units, then solve it exactly. How do you solve it exactly? You take your equation. Once you found your equation, say you have x homogeneous is equal to trying to go fast is never good. That would be for an undamped oscillator, what I just wrote, right? That's the undamped case. Then I would say, okay, at time equals 0, x homogeneous of 0 is equal to a cosine of 0 plus b sine of 0 equals a. And so I know right away that would be 5 meters. And then I would have to go to my next boundary condition, x homogeneous dot is equal to minus omega naught a sine of omega naught t plus omega naught b cosine of omega naught t. I took the derivative, and then I would set x dot h of 0 equals and so that's how I would find B. Okay, it only took 2 minutes to go through that math, because for the undamped case, it was simpler. If you have a damped oscillator, you have the e to the minus alpha t multiplied by everything, which means when you take the derivative, it's a little more complicated. But that's how you apply the boundary conditions. So this here is called applying boundary conditions. Okay, now for my final 2 minutes. Something that I was debating if I was going to hold you responsible for this or not. I'm not going to, because there's not enough time to go into depth. We can use differential equations. Well, it's not really differential equations, it's just calculus, to find an equation for a wave on a string. You have to use the small angle approximation, and you use Newton's second law on this little piece of string. So if I take this and define x directions like that and y directions like that, on this piece of string, I'd have sum of the forces in the x direction is equal to what's pulling it forward. If I have the same tension everywhere, what's pulling that string forward? Look at the picture. There's 2 forces, tension down here and tension up there. What's pulling it forward to the right? A component of the tension. Tension times what? Tension times cosine of theta 2. And what's pulling it to the left? If I have a transverse wave, the piece of string shouldn't be accelerating horizontally, only vertically. And so that should be 0, which brings us right away to cosine theta 1 equals cosine theta 2. Now, we saw this in the small angle approximation, so those should have both been 1, so that should have been true, but just showing that that would be true. And then we do the interesting part. Sum of the forces in the y direction equals, and what do I have pulling upward in this picture? T sine of which angle? And what's pulling down? T sine theta 1. And that's equal to, since it has a mass of dm, I'm writing dm, times the acceleration, which would be d second y dt squared. Right? Now, one thing you have to do here that's different from what we're used to, we're going to have derivatives with respect to time and derivatives with respect to x. So we actually need to use the partial d's here, like that. And this dm is actually going to be mu dx with the partial as well. This is the trickiest part of the entire derivation. Sine theta is approximately equal to tangent theta is approximately equal to dy dx. And so what I have in parentheses is going to be dy dx at position 2 minus dy dx at position 1. But if I have the difference for a very small range of these derivatives, not it equals, that's what the left side is equal to. The tension times the derivative of d dx, or dy dx. And the last step is dividing both sides by tension dx. And so you get d second y dx squared is equal to mu over tension d second y dt squared. And that is the wave equation. That's the equation that you have to have for a wave to travel down a string. It doesn't have to be sinusoid, but it has to fit that. So here you can see it worked out. And like I said, I'm not going to give you this. I almost put one on the test, but I said I better wait till after class. And so what I would have you do, if this were to come up, which it won't, is I would have you take a function like this and check to see if it obeys that equation. And so I would just say, well, what's the second derivative with respect to x? What's the second derivative with respect to time? Put them in and see if it works out. Okay, we're already out of time, so in fact, I've gone over. Sorry about that. I'll see you in an hour and a half for lab.